Today, we're going to be discussing enthalpy changes, the property that allows modern air conditioning or refrigeration to be possible. Enthalpy H is a way to talk about the energy in a system, especially when things are heating up or cooling down. Think of it as the total heat content of something. When a chemical reaction or physical process happens, the change in enthalpy, delta H, tells us if the reaction absorbs heat, endothermic, or releases heat, exothermic. It's like checking whether a process makes things hotter or cooler. I find it easiest to remember it being H by emphasizing the TH in enthalpy. Technically, enthalpy is a measure of the total energy of a thermodynamic system, including its internal energy plus the product of its pressure and volume. It's defined by the equation H equals E plus PV, where H is enthalpy, E is the internal energy of the system, P is the pressure, and V is the volume of the system. When a process occurs at constant pressure, such as in the room you're sitting in, the change in enthalpy, delta H, is equal to the heat exchanged between the system and its surroundings. This is why enthalpy is often associated as heat. When we measure enthalpy changes, we are looking at the difference in enthalpy between reactants and products during a chemical reaction or physical change. Heat Q and temperature T are related but different concepts. Heat is a form of energy transfer between a system and its surroundings due to a temperature difference and is measured in joules J, while temperature measures the average kinetic energy of the particles in a substance. In the air conditioning example, the air conditioner absorbs heat from the inside of your room, making the air cooler, temperature change as a result. This heat is then transferred to the refrigerant, a special fluid that changes from a liquid to a gas as it absorbs heat. The gaseous refrigerant carries the heat outside, where it releases the heat into the outdoor air. Once this is complete, it's condensed back into a liquid, and this cycle repeats, continually removing heat from your room and keeping it cool. In air conditioning, the change in enthalpy, delta H, represents the heat energy involved in the process of moving heat from inside a space to the outside, while temperature is an indicator of how hot or cold a substance is and is measured in degrees Fahrenheit F, Celsius C, or Kelvin K. Since the temperature of a substance is directly proportional to the average kinetic energy of its particles, as the kinetic energy of the particles increases, so does the temperature. For example, when you heat water on a stove, you are adding heat energy to it. This added energy increases the kinetic energy of the water molecules, which in turn raises the temperature of the water. In chemical reactions and physical changes, energy is either absorbed from or released to the surroundings and are classified as either exothermic or endothermic. This energy transfer can be observed as a change in temperature. Exothermic processes release energy to the surroundings, usually in the form of heat or light. The heat causes the temperature of the surroundings to increase, and the light can illuminate the surroundings. A great chemical reaction example of this that you can see and feel is the use of space heaters often seen at outdoor events or restaurants. These space heaters use the combustion of propane, C3H8, to release heat and light flame to the surroundings. The reaction is C3H8 plus 5O2 going to 3CO2 plus 4H2O plus heat and light. When you are near a propane flame, heat is transferred directly to your skin. The molecules in your skin gain kinetic energy from the heat, which increases the temperature of your skin. Endothermic processes absorb energy from the surroundings, causing the temperature of the surroundings to decrease. A great physical change example of this that you can feel is ice melting. Ice is water in its solid state, which means that the molecules are arranged in a structured, rigid lattice. When ice melts, it transitions from a solid to a liquid. This process requires energy to break the bonds holding the water molecules in the solid structure. This energy can come from the air. Place your hand above a stack of ice, you can feel the air is colder, or from your skin. Grab an ice cube quickly. The cold you feel is heat being transferred from your skin to the ice. The reaction is heat plus H2O solid going to H2O liquid. Most combustion reactions are exothermic because they release energy and the reactants form more stable products with lower potential energy. However, the combustion of nitrogen N2 is endothermic. Looking closer at the bonding structure of the nitrogen molecule, we can see why this is the case. Nitrogen molecules have a triple bond, the strongest out of the 3 covalent bonds, between the 2 nitrogen atoms. Breaking this triple bond requires an enormous amount of energy, more than the products N2 plus O2 going to 2NO of the combustion reaction. Therefore, since the net energy is required and not released, it's endothermic. The relative stability of reactants and products plays a crucial role in determining whether a chemical reaction is endothermic or exothermic. This can be understood through the concepts of chemical potential energy and enthalpy. Potential energy is a form of energy that's stored in an object or system due to its position, arrangement, or state. You can think of it as the energy something potentially has. Books on a shelf have potential energy due to their position and gravity, but because that shelf is holding them against gravity, it's just potential. This is the same for chemicals, which we call chemical potential energy, and is the energy stored within the chemical bonds of molecules and atoms. In a chemical reaction, reactants are converted into products. Each substance involved has a certain amount of stored chemical potential energy in its bonds. More stable compounds have lower potential energy, while less stable compounds have higher potential energy. Consequently, chemical reactions tend to move toward a state of greater stability by forming products that are more stable than the reactants. Chemists visualize these potential energy changes between reactants and products of endothermic and exothermic reactions through energy profiles, also known as reaction coordinate diagrams. They also illustrate the activation energy, the minimum energy required for the reaction to start, and the energy released or absorbed for the overall reaction. In an exothermic reaction, the products are more stable than the reactants. This means that the products have lower potential energy compared to the reactants. For example, with the combustion of propane, the products CO2 plus H2O are more stable and have lower energy than the reactants C3H8 and O2. Since the products are more stable, lower energy, the excess energy is released to the surroundings, often in the form of heat and light. The change in enthalpy is negative, delta H less than 0, since delta is a symbol denoting final minus initial. Looking at the reaction coordinate, we can arbitrarily give the products any number lower than the reactants, and delta H will always be less than 0, indicating that energy is released. In an endothermic reaction, the reactants are more stable than the products. This means that the products have higher potential energy compared to the reactants. For example, with ice melting, the products H2O liquid are less stable and have higher energy than the reactants, heat plus H2O solid. Since the products are less stable, higher energy must be absorbed from the surroundings to drive the reaction. With endothermic reactions, the change in enthalpy is always positive. Delta H is greater than 0, indicating that energy is absorbed. As discussed previously, when a reaction occurs at constant pressure, the change in enthalpy is equal to the heat exchanged between the system and its surroundings. This is referred to as the standard enthalpy change for a reaction, delta H naught, and the units are kilojoules per mole and can be determined from the change in temperature of a pure substance. These temperature changes indicate whether a reaction is exothermic or endothermic and can quantify the energy changes involved. This is often done using a calorimeter, which measures the initial and final temperatures of the water that a reaction is conducted in. From the changing temperature, you can calculate the heat Q absorbed or released using the formula Q equals M times C times delta T, where M is the mass of the water, C is the specific heat capacity of the water, 4.18 kilojoules per kilogram per Kelvin, and delta T is the change in temperature. We've discussed all these terms before other than specific heat capacity. Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin. Once you have Q, you can use the equation delta H equals negative Q divided by N, where N equals the number of moles of the substance, not water, involved in the reaction, to calculate the enthalpy change delta H. Let's run through an example with the neutralization of the acid-base reaction of vinegar by baking soda. Vinegar is approximately 5% by volume acetic acid, CH3COOH, a weak acid, and baking soda is sodium bicarbonate, NaHCO3, a weak base. The reaction between the two is CH3COOH plus NaHCO3 going to CH3COONA plus H2O plus CO2. You set up the reaction in a styrofoam cup with a stirrer, lid, thermometer, and 100 milliliters of vinegar. You record the initial temperature, 22 degrees Celsius, and add 10 grams of baking soda, replace the lid, and start the stirring. The final temperature is 24 degrees Celsius, a change of 2 degrees Celsius or 2 Kelvin. Now we measure Q with the formula Q equals M times C times delta T. The mass of the water M equals 95 grams because 5% acetic acid means 5 milliliters, 95 milliliters left, that's water. We're disregarding the water being formed by the reaction for ease of calculations, and the density of water is 1 gram per milliliter. So Q equals 95 grams of water times 4.18 kilojoules per kilogram per Kelvin times 2 Kelvin. Before we multiply across, we must first convert the grams of water to kilograms to keep the units consistent, which we can do by dividing by 1,000, and we get Q equals 0.7942 kilojoules. Now we need to determine N, the number of moles of the substance, not water, involved in the reaction. To do this, we divide the mass of acetic acid by the molar mass of it, 60.06 grams per mole, but we just have the volume, 5 milliliters. To convert volume to mass, we use the density, which is approximately 1.049 grams per milliliter for acetic acid. So 5 milliliters times 1.049 grams per milliliter equals 5.245 grams of acetic acid. 5.245 grams divided by 60.06 grams per mole equals 0.0873 moles of acetic acid. Plugging these values into delta H equals negative Q divided by N, we get negative 0.7942 kilojoules divided by 0.0873 moles, which equals negative 9.094 kilojoules per mole. Notice that it is negative, delta H is less than 0, which means that it's an exothermic reaction, which coincides with what we just saw, the release of energy. If you were to compare this to what is expected from theoretical values, you'd likely see a higher value theoretically. This is due to various factors including heat loss to the surroundings, thereby not being absorbed by the calorimeter's contents. Additionally, the calorimeter itself, our styrofoam cup, absorbs some heat which is not accounted for, incomplete neutralization of the substance being tested, inefficient heat transfer from the reaction to the water, evaporation and condensation during the experiment, and finally, inaccuracies in measuring temperature and mass can cause the discrepancies between theoretical and experimental values.